Hello and welcome to this video. In this video we are going to discuss big O notation. Okay, so let's get started. Big O notation is used to measure how running time or space requirements for your program grow as the input size grows. Okay, as we can see in this graph, we have input data size along the x-axis, and we have time, or you can also have space along the y-axis. And if you traverse towards the right along the x-axis, our data size increases, and same is true for y-axis. Like if you go traverse upwards along the y-axis, the time required or space required keeps increasing. So now let us try and understand what space and time complexity means. Time complexity, it measures code execution time. So if you write some code and the amount of time taken by the code, that basically gives us time complexity. Time complexity shows how optimized your code is, which makes your code better and makes the code to run fast. So basically, if you want to write code or algorithms, that takes less time, because time obviously is money, right? And the same thing is true for space complexity as well. Now space complexity means the amount of space needed to run the code. Okay, space complexity also makes your code more optimized. So both these things, space and time, are the lesser it is, the better our algorithm or our piece of code is, right? Now let us look at constant time complexity. It is represented by capital O, and in parenthesis we have 1. Algorithms or operations are considered to have a constant time complexity when they are not dependent on the size of the input data, and the time required is the same every single time. For example, suppose if you have something, or if you write an algorithm where or an operation where it doesn't matter, even if you have a small data size or a large data size, the amount of time that will be consumed while running that operation or algorithm, if it is the same in both the cases, we call it to have a constant time complexity. Addition, subtraction, assignment, and most forms of basic lookup are considered to run at constant time. So when you see these types of operations, make a quick mental note that they run at constant time complexity, right? So as you can see that in this graph, as we go towards the right, our value of n increases. However, the time is not increasing, it is constant. Next we have linear time complexity. It is represented by capital O, and in bracket we have n. Algorithms or operations that have a linear time complexity can be identified by the fact that the number of operations increases linearly with the size of the input. That means if an operation has to run 100 times for a list that's 100 items long, then it has linear time complexity. Say for example, if you have an array of 10 elements, okay, and it is taken, and you write some algorithm, and the algorithm takes 10 seconds to run, and now if you have like 50 elements, now the execution time is going up to 50. That means it is directly or linearly related to the amount of data size, right? So for loops are a great example of an operation that has linear time complexity. Next we have quadratic time complexity. It is represented by capital O, and in parenthesis we have n square. Quadratic time complexity represents an algorithm whose performance is directly proportional to the squared size of the input data set. For example, if you have in this graph, if you suppose you write an algorithm or some operation to run, and the data size is 2 data values, okay, or 2 elements. So and we see that the time taken is suppose 4 seconds. Now if we increase the data to 3, data size to 3, then we are observing that the time taken is 9. So we can clearly see that it is like growing exponentially, like it has a proportional relationship which is equal to the squared size of the input data set, right? So in such cases we call that operation or algorithm to have a quadratic time complexity. Next we have logarithmic time complexity. It is represented by capital O, and in parentheses we have log of n. Logarithmic time complexity basically means time goes up linearly while the n value goes up exponentially. So if it is taking 1 second to compute 10 elements, it will take 2 seconds to compute 100 elements, 3 seconds to compute 1000 elements, and so on. And these are just examples. Okay, so in the graph we can see that suppose we have 1 in here, 1 second. This is an corresponding to 1 second. Okay, and if we increase it, suppose same this much is representing 1 second, so approximately this will be representing 2 seconds. Okay, right? So you can see that if we correspond the n value here, suppose n value is here, right? It is some value that is accounting to this much space. Okay, so now if you go to 2 seconds, we can see that the n value is somewhere like I have it's a mess. Wait, let me fix things. Okay, so if I go to the n value corresponding to execution time 2, we can see that we have a much greater input data size compared to this. So so as we can see that the relationship is such that the input size grows exponentially, but the execution time is growing very slowly. Okay, or it is growing linearly. Okay, in such cases we call the algorithm or the operation to be following a logarithmic time complexity. So the common time complexities are the constant time complexity, log of n, which is the n is the data size value, then linear time complexity, log linear time complexity, quadratic time complexity, cubic time complexity, and exponential time complexity. And we can see that the best one is the constant time complexity, where it is independent of the data size value. Okay, then we have the log time complexity, then we have linear time complexity, and so on. So the worst one is when we have a exponential time complexity, because just by small changes in the data size we have huge amount of time difference. Basically the amount of time taken even by a small change in data size is like enormous. Therefore that is the worst case that we can have, right? Because we know that time and space are crucial. We want to minimize them as much as possible, so our algorithms should be such that it is taking lesser time and lesser space. Okay, so this is it for this video. In the next video we will look at arrays and how to work with them, and we'll probably solve questions related to arrays. And yeah, I think that is it. So I'll be ending this video, and I hope to see you guys very soon. Thank you for sticking by.